yeah, good morning. So we're going to talk to Robert afterwards for will be speaker dinner tonight. I think I first ran into Robert must have been close to 20 years ago now. I think it was in Texas for 1 year. And yeah, always very interesting to hear Robert's latest insights into all the big questions in cosmology, and we're just kind of about another interesting twist on things that are all around us.
So this title is meant to be a bit provocative. Alternatives to cosmological inflation from quantum gravity. So most cosmologists are working under the assumption that inflation is part of the standard paradigm. So what I want you to do for this talk is to carry away some concerns about this, whether we should really consider inflation as having been established. So I'll be giving you my list of worries about inflation. Now I'm going to go on, actually, the list of worries is not so satisfying. I'm also going to give you alternatives to inflation. These alternatives will address a couple of the worries that I raise about inflation. But I also want you to be a little bit skeptical when I talk about the alternatives. So I would like you to walk away having seen what I'm concerned with. So please take that part of this talk seriously. I claim that these are really things we ought to be worried about. And then hopefully you'll be amused at the second part. You shouldn't take that too serious, because the alternatives which I'll present, they might be interesting, they're interesting to me, but they're not as well established as inflation yet, because many fewer people are working on it. So I'm going to start with a fairly lengthy introduction. Well, first of all, remind you what inflation is, and then I'll give you my list of conceptual problems for inflation and cosmology. And the message of that part is that we should keep an open mind to alternatives. So the two alternatives which I'll present are, firstly, string gas cosmology. And string gas cosmology is based on ideas from superstring theory. And then the second alternative is what I call the matter bounce scenario. And this might be realized in a new approach to quantum gravity, which is called Rojava difference gravity. So this is the outline. So first of all, the lengthy introduction, and hopefully with questions, this will probably take half the talk. So you all know that the inflationary universe scenario is the current paradigm of early universe cosmology, because a lot of you are working under the assumption that this is part of the paradigm. Why is it the paradigm? Well, it solves some problems with the previous paradigm, and the previous paradigm was standard Big Bang cosmology. So it solves the horizon, flatness, and size entropy problems. Those are problems of the standard Big Bang. But what really made inflation into a good theory is that it made predictions. It gave the first causal generation mechanism of cosmological perturbations, and this causal generation mechanism was predicted. So, whenever someone presents an alternative to inflation, the alternative better also be not only post-predictive, but at least a little bit predictive. And for both of my alternatives, I'll give you some small predictions as well. So this is now the map that you all are familiar with, the temperature map with the microwave background. We can quantify this by expanding the map in spherical harmonics and plotting the power in each spherical harmonic. So power, spherical harmonic. And what I want to emphasize is that the red curve, which is the prediction of inflationary cosmology, was already there in the early 1980s. In fact, Dick was one of the main contributors to that. And then much later came the data, which are the black points with the statistical error bars and the systematic uncertainties. So you do have to fit a couple of parameters to get this excellent fit. But this is really a triumph for cosmology, for theoretical cosmology. So from a phenomenological point of view, inflationary cosmology is in great shape. And I'm not going to criticize inflation on that point. So I'm going to mention some conceptual concerns. And what I want you to walk away with, given these conceptual concerns, is that we should keep an open mind for alternative scenarios. And these alternative scenarios might lead, or these alternative ideas might lead to a better realization of inflation, or they might lead to an alternative to inflation. And I'll be pursuing the latter route. So these alternatives have to be based on new ideas in fundamental physics. And I will explore two alternatives, string gas cosmology and the matter balance. And I want to emphasize that each of these alternative scenarios will make predictions with which these scenarios can be differentiated from inflation. Specifically in the case of string gas cosmology, I will give you a prediction concerning gravitational waves. And if the predictions come in line with what is predicted in string gas cosmology, then all inflationary universe models are ruled out. So inflation is falsifying. You should also walk away from this talk with the realization that inflation is falsifying, which again means that it's a good theory. So, brief review of inflationary cosmology. We start with general relativity as a theory of space and time, and we add some matter. And we add scalar field matter because we want to have a phase of exponential, almost exponential expansion. And if you work in the context of general relativity, then in order to get this phase of almost exponential expansion, you need matter with this equation of state. Pressure almost equal to minus energy density. And in terms of the particle physics that we know, you seem to require scalar fields for that. And not any scalar field. The Higgs field will not do. You need a scalar field with a very soft potential such that the scalar field will roll very slowly. And you need that, first of all, because you need potential energy to provide for inflation, and you need this potential energy to dominate for a long time, and therefore you need this scalar field to be slowly rolling. So, the timeline of inflationary cosmology, you have a period of finite duration of acceleration. Before that, you had a Big Bang singularity, and then you had standard cosmology. And what will be very important in my talk, when I present alternatives, is space-time diagrams. So this space-time diagram I will use several times, and I will show you the corresponding space-time diagram of string gas cosmology and the matter balance. So this is time, this is physical distance in space, and the Big Bang, the finite duration period of inflation, and the post-inflation phase of standard cosmology. And I have three length scales. First of all, I have the horizon. And by horizon, I mean the causal horizon, the maximum distance that could have been in causal contact beginning at the Big Bang. So it's a distance light could have traveled from t equals 0. During the period of exponential expansion of space, the horizon is increasing exponentially. So this is the causal horizon. The second distance is the Hubble radius. And the Hubble radius is a local quantity. At any given time, the Hubble radius is defined as the inverse Hubble expansion rate. And it is very important that the Hubble radius is not equal to the horizon. In fact, the reason why inflation solves the horizon problem is precisely because the horizon is exponentially larger than the Hubble radius. And many cosmologists use horizon when they talk about Hubble radius. And that causes a lot of confusion to everyone. So please don't use horizon when you read Hubble radius. Any alternative to inflation will have this same difference between horizon and Hubble radius. Finally, the third distance is a physical length that corresponds to fluctuations which you all are observing. For example, particular scales of the microwave background, their physical wavelength is expanding as the universe expands. Okay. Now, the reason why inflation can provide a causal mechanism of structure formation is that all scales that we observe today start out smaller than the Hubble radius at the beginning of inflation. Therefore, a local microphysical generation mechanism is possible. And I will illustrate this later with equations. Why is the Hubble radius that's important? So inflation renders the universe larger because it's spatially flat. Classical matter redshifts, and therefore, when we calculate fluctuations in inflationary cosmology, we assume that fluctuations start out in their quantum vacuum state. This is justified because classical matter that is present at the beginning of inflation redshifts, leaving you maybe with a matter vacuum. Then working under the assumption that we start with quantum vacuum fluctuations, GBs of a movement of calculated the resulting spectrum of microwave anisotropies, and they found this red curve which I showed you before. So far so good for inflation. Now here's my list of conceptual problems for inflation. And I want to highlight the latter four. So first of all, particle physicists will ask, what is the scalar field that gives rise to inflation? No particle physicist has ever discovered a fundamental scalar field in nature. And even if the Higgs is present, then with the standard coupling of magnetic gravity, the Higgs field cannot be treated onto it. Now, even if a particle physicist gives you a scalar field, this scalar field has to have the right conditions. It has to have a potential which is sufficiently flat. It has to couple correctly to matter so that we get a universe filled with regular matter and not an empty universe after inflation. And then you have to have initial conditions which are offset from the minimum. Even if you buy that, you typically get the wrong amplitude of cosmological perturbation. You have to tune the particle physics model to get the right amplitude. So these are all maybe parallel problems. So I want to focus on these problems. First of all, the singularity problem. So we knew before inflation was developed that standard Big Bang cosmology was incomplete because there was an initial singularity. This is what Penrose and Hawking proved using general relativity coupled to matter satisfying the usual energy conditions. Quite strong energy conditions. Border and Vilenkin, and later Border, Vilenkin, and Good extended the Penrose-Hawking theorems to apply to classical scalar field matter. So, if you define inflation as I did, namely general relativity coupled to matter, then inflation has an initial singularity and therefore it's incomplete. Now, the transplanting problem, this is a problem which always gives me a headache when I try to persuade the audience in seminars, but I keep doing this. And in a couple of transparencies, I have some strong support in terms of the quote. Anyway, let me try to explain the problem. So this is the same space-time diagram that we saw before, but with one extra scale. And this extra scale is the Planck length, or the string length of your string case. So now, the only thing we know about quantum gravity for sure is that we don't understand physics on wavelengths smaller than the Planck length. But the success of inflation relies on the fact that the physical wavelength of perturbations which we observe today is exponentially increased during inflation, as indicated with the red line. So, now if inflation lasts for more than 70 times h inverse, where h is the Hubble expansion rate during inflation, then all scales that you are all observing today in the universe, even the largest scales that we will ever observe, start out with wavelength smaller than the Planck length at the beginning of inflation. So therefore we have no right to use general relativity coupled to classical scalar field matter to analyze fluctuations in this zone of ignorance. New physics must enter into the calculation of fluctuations. I can't tell you how, because I don't know what the theory of quantum gravity is, but I know that new physics must enter into the calculation. This is a transplanting problem for fluctuation. Now, the quotation I have is in a paper by Linde, Mukhanov, and Wickman. And they say that it is not sufficient to show that during inflation the Hubble constant is much smaller than the Planck scale. If the frequencies involved in the analysis of cosmological fluctuations are many orders of magnitude larger than the Planck mass, as they are for inflation, then the methods used in the standard analysis are inapplicable for the description of the process of generation of perturbation in scenario. Okay, that's a quotation in this paper. Now, those of you who know Andre Linde will obviously realize that Andre Linde wrote this quotation not talking about inflation, but talking about an alternative to inflation. But one should be consistent. So, this is the quotation. Okay. So now, Jérôme Martin and myself, we invented toy models of physics that happens on transplanting scales based on modified dispersion relations. And we were able to show that if the toy model gives you evolution which is non-adiabatic from the point of view of the wrong theory, then you can get large deviations from the standard predictions. You get a large tilt. Because short wavelengths undergo the non-adiabatic evolution for longer time than the long wavelengths. They get amplified more and you break the symmetry that usually is responsible for giving you the skin band spectrum. So this,
Big promise to be the defender of the
yeah,
space.
he's been very quiet.
He has been defending, so I will defend it for him.
Great.
So, I mean, yes, I hear you, what you're saying. Now, in some sense, yes, there are these problems. I'm not proposing that there are these problems, but if you just look at the historical evolution, that in a pre-inflationary Big Bang picture, there was also the singularity problem, and there was also the transplantation problem. They were all there. And you know, I would argue, yes, they were always there, and they always have been there. It's not really worse than inflation; it's just still there, right?
I completely agree with what you said. But in what the two alternatives which I will present, the fluctuations are always on wavelengths much larger than a Planck length. So the fluctuations in the two alternatives which I will present never probe the transplanting zone of ignorance. So these alternatives have other problems with them.
I do have to step in. I mean, the first point is that where preheating occurs, the co-moving length scale now is the order of a centimeter, maybe a bit.
Yeah, that's right.
So then you project that back and
that's
you're
why
there.
Yeah.
But if you look at the large scale structure regime, it's not clear that there's any transplanting when you project back. Right? It's actually a really short distance issue. But then
wait a minute, no, don't do that. So I'm taking the larger scales that we observe today, and if inflation lasts more than 7 years, remember the physical wavelength at the beginning is smaller than the Planck wave. I'm talking about the smallest scale.
I was dealing with 50 to 60, so everything.
Okay, if you have a fine-tuned inflationary model where you're 50 to 60 fold inflation,
No,
this
I
problem
mean
doesn't
the
arise.
length scale that we are currently able to observe on the large scale. But here is the issue which I am completely in agreement with, which is that the standard assumption of inflation is that we have these essentially time-forward outgoing waves that are essentially acting like particle oscillations with an e to the minus IET. And that is always been an Achilles heel. There was always discussion about how to get around it. The problem is, to this day, in spite of the fact that that was, certainly back in the early work I did on this, we were pointing to this. We don't know if we're making this assumption. Until your suggestions, of course, but there has not been a concrete way to go after that. And I think that's still the case today.
They're concrete, but not so well quantitative yet.
Yeah, I mean,
toy models,
yeah.
which can study the sensitivity.
Right.
That was what I'm.
One of the issues is that whether you have these high frequency oscillations, the fact that the energy scale of those oscillations is very small and perturbative, does that mean that the fact that the length scale is so short that that's going to screw things up?
There are toy models where it can.
Yeah, okay.
Okay. So now another concern is the fact that in toy models of inflation, the energy scale that inflation occurs at is quite high. It is much, much closer to the string scale and the Planck scale than to the scales that we observe. Now we know that in all approaches to quantum gravity, the Einstein action is only the leading term in the low curvature expansion. And at the string scale and the Planck scale, the Einstein action doesn't provide the most important term. So, the scale at which inflation happens might be too close to the Planck scale or the string scale to trust the predictions made using general relativity. Here you see, I'm saying might be. It's a much I'm making a much deeper statement here. But this is a concern. And one thing that, at least for some people, is the Achilles heel of scalar field-driven inflation following. So we know that a free scalar field has quantum vacuum energy, a large quantum vacuum energy. But we also know from observation that this large quantum vacuum energy of scalar field does not gravitate. We don't know why it doesn't gravitate. That's a cosmological constant problem. Now in scalar field-driven inflation, we are using exactly the part of the potential energy, which looks exactly like quantum vacuum energy, and coupling it in the usual way to general relativity in order to get inflation. So if there's some mechanism like degravitation, which says that some contribution to the potential that's homogeneous doesn't gravitate, then you might wipe out all of scalar field-driven inflation. And I heard that the reason Henry Tye did not put his name on what became the Booth paper of inflation, that he was worried about this point.
But by the same token, I'm not saying that, I mean, this actually exacerbates the issue. The same issue is actually here for every single centimeter of space in this
But
room.
here,
There are all of these oscillators that should have all of this energy, and we magically say, we are Minkowski, and Minkowski doesn't experience this.
Right.
And then we put in, with curvature, we put in a response to it in ways that are a bit mysterious. So, I mean, it is an issue which is at the heart of quantum field theory. It's not just...
And it's at the heart of coupling quantum fields to gravity. So the cosmological constant problem is not important for accelerating experiments, but as soon as you couple quantum fields to gravity, it is. So now this slide summarizes some of these conceptual problems. There are various windows of ignorance, the low, small wavelength zone of ignorance, and the high density zone of ignorance. And in models of inflation, where inflation lasts for more than 70 foldings, the scale of fluctuations penetrates this zone of ignorance, and the scale at which inflation occurs is uncomfortably close to this zone of ignorance. So I don't want to claim that these are fatal for inflation at all, but these are problems for inflation, and what I want you to carry away from this part of the talk is that this motivates the search for alternatives. And also, if you really like inflation, then you should also have a completely independent reason for liking the search for alternatives. Because any reasonable search for alternative, any alternative which cosmologists should take serious, it will make predictions with which it can be differentiated from inflation. Otherwise, it's not a good alternative. So the more alternatives you have, the more things you can go after in terms of observations. And therefore, then if the observations come out the way that inflation predicted them, inflation will be on front of you. Like what happened when inflation ruled out topological defect models as a competing theory. So hopefully you will now have enough motivation to listen to the second half of the talk, where I'll be looking for alternatives. Okay, and I'll be presenting string gas cosmology, which is based on some ideas from superstring theory. When I realized that I forgot something very important, I've got a prop. Now, could you maybe go and fetch my prop? Just could you go to the secretary's office and get an elastic band? Or maybe someone has an elastic band. So just, because strings after all are like elastic bands. So there's something I want to illustrate with elastic bands. I have my second prop here. It's a piece of paper. Okay. So this string gas cosmology is based on some fairly naive ideas about superstring theory. The second alternative is the matter bounce, and the matter bounce can be realized in Bouchard-Lifshitz gravity and also in the ghost condensation mechanism. And I'll show how these two alternatives give rise to some specific predictions. Okay. Now, predictions will involve cosmological perturbations. So I have to remind you how the theory of cosmological perturbations works. So I'm interested in perturbations of matter and of the metric, and they are tied together by the axiom constraint equations. fluctuations are small today on large scales, and since gravity is purely attractive, fluctuations were even smaller in the early universe, and therefore we can hope to do linear perturbation theory. Now what linear perturbation theory shows us, and I will demonstrate this using equations, is that on sub-Hubble scales, matter fluctuations dominate, on super-Hubble scales, metric fluctuations dominate. Next slide. Okay, so let's go back to inflationary cosmology. Fluctuations emerge on sub-Hubble scales, where the matter moves around stuff, and then fluctuations propagate for a long time on super-Hubble scales. And that propagation on super-Hubble scales is important for generating the coherence that gives you the nice acoustic oscillations in this angular power spectrum of microwave background. So I maintain that any alternative to inflation has to have this feature that fluctuations emerge on sub-Hubble scales and that they propagate for a long time on super-Hubble scales. Okay. Now how do we do this theory? Yeah, I refer you to this review article by Salomon and Hugh Feldman, who was one of the early postdocs here. CITA, in this review article we actually wrote while he was a postdoc here. So we take the metric and we pick a particular coordinate system and we introduce space and time dependent small amplitude fluctuations. That's the red. So this phi is space and time dependent. It is a scalar metric fluctuation. This is matter. This is the matter fluctuation. So blue is the background, only time dependent. Red is the space and time dependent fluctuation. Now, the two perturbative degrees of freedom are related by the Einstein constraint equation. Therefore, there's only one fundamental degree of freedom. So if we want to do linear theory of cosmological fluctuations, we have to expand the action to quadratic order, and we know without doing any calculation what the form of the action will be. The action for cosmological perturbation for the variable b will take the form of a free scalar field with a time-dependent mass. We get linear equations because we do linear cosmological perturbation theory. There's one degree of freedom. The only non-triviality is a coupling of this perturbation variable to the non-trivial background. That's given in terms of the time-dependent mass. So now we have to do a very tedious and complicated and straightforward calculation to find what this variable is that has canonical normalization. And this is the so-called Sasaki-Mukhanov variable, and it is this combination of the matter fluctuation and the metric fluctuation. And the time dependence of the mass is set by essentially by the scale factor. If the equation of state of the background is time independent, then Z is proportional to the scale factor. So this is the action for cosmological perturbations. This is the resulting equation of motion in Fourier space. And from this equation of motion, we deduce that on scales smaller than the Hubble radius, this term dominates over this term. The magnitude of this is essentially h squared. So on sub-Hubble scales, fluctuations oscillate like they would do in flat space-time. But on super-Hubble scales, where this term dominates over this, the microphysical oscillations squeeze out, this is unimportant, and fluctuations coast along as described by the background. This is squeezing that appears on super-Hubble scales. And in an expanded universe, dk is proportional to the scale factor. Now, if we start with vacuum initial conditions, this is the initial quantum vacuum amplitude for the fluctuations. Harmonic oscillator ground state. So this is the theory of cosmological perturbations in a nutshell, and this is applicable not just to inflationary cosmology, but to any theory in which the perturbations are linear. Initial conditions, equation of motion. And then how we relate the variable to the physical variables that you are all observing. Okay, so in inflationary cosmology, we start with quantum vacuum initial conditions, as I justified earlier. And these then propagate and are squeezed on super-Hubble scales, giving rise to the coherence that gives rise to the angular, gives rise to the acoustic oscillations in the angular power spectrum of microwave background. So now I'll present you the space-time diagram in string gas cosmology without having told you what.
So are you ascribing to this Sterolicious view that the squeezing is enough to give you the classical
No, it's not enough.
rather than the...
It's one of two necessary ingredients. The other is decoherence.
Yeah, so you aren't saying decoherence isn't necessary.
No, I'm not, but Stravinsky isn't says either. It is most recently.
No, I know, but the people that work with them essentially...
But I mean, the standard paper that I'm referring to is a paper by Polarski, Kiefer, and Stravinsky in 2006.
Yeah, but very recently Polarski wrote a review of that work in which he was more interested in the squeezing issue rather than...
No, I think that both are
Yeah, absolutely.
crucial. Okay. Okay. So now in string gas cosmology, the universe begins with a static phase, or an almost static phase. And in the static phase, h is equal to 0, and therefore h inverse, the Hubble radius, is infinite. In the static phase, the physical wavelength of perturbations doesn't change. So the temperature at the end of the static phase is approximately the same temperature as the temperature at the end of inflation. So the post T sub r evolution is like in standard Big Bang cosmology, like in inflationary cosmology, but instead of having the inflationary phase, in string gas cosmology we have a phase in which the physical wavelength of perturbations is constant, and as Dick said, this means that it's centimeter millimeter scale. The Hubble radius is infinite, however. So perturbations are generated on sub-Hubble scales, and they propagate for a long time on super-Hubble scales. And so if we can show that we get the scale-invariant spectrum of cosmological perturbations, we will have the coherence that will give us the acoustic oscillations of the microwave manifold. And now this is the space-time diagram in the matter-bound scenario. Here I draw the scale factor as a function of time. It is a symmetric scale factor. We start in a matter-dominated phase of interaction. Then there's the time minus TeQ, where there's a transition to the radiation-dominated phase of interaction. Then there's a new phase, a non-singular bounce, which I'll have to construct for you at the very end of the talk. And then there's standard cosmology. And this is what the Hubble radius does, now improved in spatial coordinates in this matter bounce. Hubble radius contracting, expanding. Scales emerge, sub-Hubble, they propagate for a long time on super-Hubble scales. So you see that I can apply the same theory of cosmological perturbations that I've applied in inflationary cosmology to string gas cosmology and to the matter bounce. And that's what I will be doing in the rest of the talk, after telling you where string gas cosmology comes from. And this is where I am in the talk. So, string gas cosmology goes back to a paper that I wrote with Truman Bafra in 1989 in prehistoric times, before the archive. So, the idea was to make use of new symmetries and new degrees of freedom, which string theory has, which ordinary point particle theory does not have. So our field theories are based on point particles, and point particles are not strings. But for those of you in the back, the very back, this looks like a point particle. But for those of you in the front, it doesn't look at all like a point particle. They are oscillatory degrees of freedom, which point particles do not have. And if this is space, strings can do something which point particles cannot do. They can wind space and keep space compact. I need a scissor in order to allow space to expand. So I want to use this aspect of string theory, these new degrees of freedom. Now, I will assume that I have some background, classical background space-time, and that matter is a gas of fundamental strings. I want to take all spatial dimensions to be compact, because I want to use the fact that strings can wind the spatial dimension. So a lot of what I will say does not hold if space is not compact. I will assume that the space is a nice torus, but I don't need that. I only do for mathematical simplicity. Okay. So the new degrees of freedom are the string oscillatory modes and the string winding modes. Now if you do the thermodynamics of a gas of fundamental strings, taking into account the fact that the number of different oscillatory modes increases exponentially with energy, you find that you can't exceed a certain maximum temperature called the Hagedorn temperature. So if you couple a gas of strings to classical space-time, you can never get to infinite temperature. Now, so let's look at the energies in the different degrees of freedom. The energies of different degrees of freedom as a function of the radius of this torus, or the size of space. See, if I take momentum modes, which point particles have in a compact space, their energies are quantized in units of 1 over r. The larger the space, the less obstruction it is to move. However, the energy of winding modes is proportional to r, quantized in units of r. The energy of the oscillatory modes of the strings is independent of r. And then we have a symmetry. If you take r going to 1 over r in string units and you change n and m, then the spectrum of mass states is unchanged. And the interactions of strings are also independent. They also obey the symmetry. And if you assume that this symmetry is fundamental to string theory beyond perturbation theory, you get the prediction of the existence of D branes. So I will assume the symmetry. And if you take the symmetry, if you take a box of strings with radius r, and you plot the temperature as a function of r in thermal equilibrium, you get this bell-shaped curve. So at large radius, most of the energy is in the light momentum modes. Then as the radius decreases to close to the string radius, the energy will populate the oscillatory modes and then the winding modes. And as the radius goes below 1 in string units, the energy will all flow into the light momentum modes. So this is the time radius curve of string thermodynamics. And this is very different from the time radius curve in standard point particle cosmology. And what I want to use for my alternative to inflation is this plot here. So there's no dynamics. This is an adiabatic consideration. And let me mention straight out that the weak point of string gas cosmology is that we don't understand the equations of motion, which describe the coupling of the string gas to the background at these very high temperatures. But there seem to be two possibilities. Either you start near this distinguished symmetric state, live there for a long time and then slowly roll off. Or else you start here and you give the system a big enough push that the temperature coasts over this barrier and comes back down. So these heuristic considerations seem to indicate that string matter coupled to gravity will lead you either to a bouncing cosmology or to what George Ellis calls an emergent universe, where the temperature as a function of time is constant for a very long time and then it rolls off. So this rolling off, we have very good control of, because the rolling off corresponds to a process of winding strings intersecting and forming loops. And loops of cosmic strings is regular radiation. So this transition, which I sketched over there, is the transition which dictates when this will happen.
So can you actually prove that it's got a Hagedorn phase? That is to say that it's actually got the number of states having that remarkable rise, which is guaranteeing that G is a constant?
Well, okay, so this adiabatic, this we can prove. This is a calculation, not just this comes from taking the string partition function and evaluating the string partition function as a function of rate.
But that's assuming the modes that you're describing.
That assumes that the string coupling constant is small, so that the string states are lighter than the brane states. So, but what I can't do is I can't give you the equation of motion that describe how this gas of strings comes to background. I know that Einstein gravity won't work because it doesn't have the right symmetries. I know that Dirichlet gravity doesn't work either because Dirichlet gravity doesn't have S-ground symmetry.
But this is fundamentally, at least...
This is a calculation.
Yeah.
And you see, here I put two different curves.
Is this fundamentally a 10-dimensional theory, or is it even before the 10 dimensions actually materialize?
This is a 10-dimensional theory because it's based on perturbative string theory. So when I say that this is established at the level of string perturbation theory in 10 dimensions. And then what I will do is I will argue that this process here can happen in at most 3 spatial dimensions because string world sheets never intersect in high dimensions. So this mechanism of rolling off will only allow 3 spatial dimensions to roll off, and the other ones would be nice and compact and stabilized at the Planck scale. That's not a mistake. Which I write down here. There are obviously some caveats in this argument. So this was a point that Rathman and I made back in 1989, that string theory gives rise to a potential mechanism for explaining why we only see 3 dimensions of space in a theory in which space has 9 dimensions. Okay, but from now on I'll be just following the 3 dimensions, the 3 large dimensions. The other spatial dimensions are stabilized. For experts, this is modular stabilization. And again, for experts, I want to stress that modular stabilization in string gas cosmology is in very good shape compared to modular stabilization in string inflation model building. Because the winding modes and the momentum modes keep the sizes of all of the extra dimensions at the string state. There's a stable fixed point. And this specifically happens in heterotic superstring theory, where there are states that have both winding and momentum about the extra dimensions, and they have 0 energy at the self-rule radius. So if we instead of looking at an isometric torus, if we introduce a so-called shape modulus, a non-trivial angle, we can follow the evolution of this non-trivial angle, and we find that this angle is smoothed out and stabilized naturally at 90 degrees. So shape moduli are naturally stabilized in string gas cosmology as well. The only modulus which is not stabilized in string gas cosmology without extra input is the dilaton. And we've used gauge-eagle condensation in order to stabilize the dilaton. And we stabilize it by adjusting the parameters in this gauge-eagle potential. We stabilize the dilaton at its weak string coupling, and we show that dilaton stabilization is consistent with the size stabilization.
So I don't quite understand how this is relating to the picture where when you're starting into the approach to compactification,
Right.
Different structures in the manifold, there aren't any basic symmetry breaking things, and it doesn't really cost you to shrink or increase the size. So the expectation is that you've got all sorts of pretty free dynamical possibilities for the evolution. And then the usual framework, which is what you alluded to, is that non-perturbative effects are the things that occur in stabilization.
No,
for you, it's not the case.
Not at all. Not at all.
So I don't quite get the physical mechanism.
The degrees of freedom. So first of all, for those of you who are not in the early universe community, I promise that I'll go back to things which are a little bit simpler later, but this is now a discussion for the experts. So what's happening is that the modes that I'm dealing with are their energy depends very sensitively on the radius and on the shape, because it's winding modes and momentum modes. It's not if you forget about if you do field theory motivated by string theory, you throw out essentially the winding modes.
So the flux flowing being sort of more macroscopic
I don't have any
description
fluxes.
is irrelevant from your point of view.
No fluxes.
That you have all of these states that are enforcing,
That's right.
but those are supposed to have been already ignored in dealing with the moduli.
But incorrectly.
Is that right?
Yeah.
So in other words, you would challenge every potential that people are writing down, or including ones that we use, for how you can stabilize, but how you can also use it to drive inflation. Do you think that we are missing something enormous here?
I think so.
We-
But you have many other, you've added many more ingredients, so maybe in your constructions those are more important. So we have no fluxes, it's a symmetric setup.
Yeah,
We have the
we
winding
aren't
mode.
even discussing the winding modes. I mean, it's all sort of flux.
Now let's talk about that, let's postpone that discussion to after the talk. Okay. So, I want to go back to this picture. So you see this is string gas, this is how the scale factor evolved in string gas cosmology. The static phase followed by the standard cosmology phase. What I want to show you now how scaling band spectrum emerges. So the non-early universe experts now pay attention. So this is the space-time diagram. This is by static phase. This is the standard cosmology expanding phase. Now, this static phase is filled with the thermal gas of strings. So we don't have vacuum initial condition. We have thermal initial condition. And it's not a thermal gas of point particles, but it's a thermal gas of strings. So, now the way that we do the calculations is the way that people in the West did the calculations of generation and evolution of fluctuations in the early days of inflation. So what we do is we go to sub-Hubble scales, we calculate the matter correlation function. Then we follow each scale until it crosses a Hubble radius, and then we convert the matter perturbations to metric perturbations. And from then on, we evolve the metric perturbations into global scales. That's a three-step procedure that we're going to follow. So this is the ansatz which we make for the metric, and we are going to calculate gravitational waves and the usual cosmological perturbations together. So this phi, that's the scalar metric fluctuations, the usual cosmological fluctuations. This tensor, which is transversal traces, those are the gravitational waves. The Poisson equation tells us that energy density fluctuations seed cosmological fluctuations. The Einstein equations also tell us that off-diagonal pressure perturbations seed gravitational waves. So what we're going to do now is we're going to take the partition function of string theory and calculate the energy density fluctuations, and we're going to calculate the pressure perturbations, and that's going to give us the cosmological perturbations and the gravitational waves.
But the K is a 3D K.
K is a 3D K.
K.
It's a 3D K. So we are now looking at time, so the 6 dimensions are stabilized at the string scale, and we're no longer following them. But the modes are still contained, so in doing the string partition function calculations, we are still carrying with the extra spatial dimensions, but we are fixing them at the string scale. Okay. So now for thermal fluctuations, the energy density perturbations are very generally given by the specific heat capacity. There's nothing stringy in this formula. This is just a general formula for thermal fluctuation. What is special for strings as opposed to point particles, and strings which have windings, is that the specific heat capacity scales as R squared and not as R cubed. So, these are all the ingredients that we need to calculate the spectrum of cosmological perturbations in string gas cosmology. And the calculation is here. It's 4 lines. Now I'm not going to go through this in great detail. So the power spectrum of cosmological perturbations is given by the energy density fluctuations, by the Poisson equations I had before. I go from Fourier space to position space, the mass perturbations, density perturbations. For the density perturbations, I put in the thermal perturbations. For the thermal perturbations, I put in those given by the thermal string gas. This is the result. K, where is K here? The K has cancelled out. So therefore, we get a scale invariant spectrum of cosmological fluctuations in string gases volatile. So now if we look a little bit harder, we have to ask, what is this T here that flows? Let's go back. This T is something in the early phase, because it is in the early phase that we have in the energy density fluctuations. So the time when we are converting the energy density fluctuations to cosmological perturbations, it's a scale-dependent time. Let's go back even further. Long wavelengths exit the Hubble radius at a very, very slightly higher temperature than short wavelength loads. So if we go back, this T is slightly larger, very slightly larger for large wavelength loads than for small wavelength loads. Therefore, we get a very slight red tilt, like for inflation. So at this point, I've given you an alternative to inflation for producing a scale invariant spectrum of cosmological fluctuations.
If I put in T, quote unquote, as an H over 2 pi, I get
Yeah.
fusion right there.
Yeah. No,
Because of the
absolutely.
1 minus T over TH.
Not only that, but you don't put in, you're putting in something that's way suppressed. The quantum perturbations are way suppressed compared to the thermal fluctuations.
Because it's
The thermal gas, the thermal fluctuations greatly overwhelm the quantum fluctuations. So now, well, if we had done this calculation in 1989, we didn't know about this calculation in 1989. Then what we would have done in 1989, we would have looked up the Bible of string theory in 1989, which is a textbook by Green, Schwarz, and Witten, and they told us what the string length is in terms of Planck length. And if we would have inserted into this formula, assuming that this factor is order 1, we would have obtained the Cobi amplitude of fluctuations. No amplitude problem. So the amplitude comes out almost naturally applied. A little bit more modestly, we have two free parameters in this calculation. One free parameter is the string length divided by the Planck length, and the other free parameter is the temperature during the Hadron phase divided by the maximum temperature. Those are two free parameters, but with these two free parameters, we are going to predict 4 observables. The amplitude of the scalar cosmological perturbations, the tilt of the cosmological perturbations, and the amplitude and the tilt of the tensor. And I realize I've been talking a bit too slowly now. So this is the corresponding calculation for gravitational waves, and for gravitational waves, we get something that at first sight looks scale invariant, but if we look a little bit more closely, we get a blue tilt, a slight blue tilt, unlike for inflation. And the reason why we get the slight blue tilt is the following. The pressure perturbations are set by the overall pressure. And earlier in time, the pressure is closer to 0. And so on large scales, we get smaller pressure perturbations than the small scale. Yeah, that's why we get a slight blue tilt. So we understand both analytically and heuristically where this slight blue tilt comes from. So this is the end of the section on string gas cosmology. This is our prediction. We get a slight blue tilt in the spectrum of gravitational waves. The other things are more or less like for inflation. And if you ever were to find a blue tilt in the spectrum of gravitational waves, you would have rolled out inflation, because inflation generically gives you a red tilt. Okay. Now here I'll be fairly short, but do I actually have, I have 10 more minutes, is that right?
You have an amplitude curve?
Yes. So if I fix the two parameters, the three parameters, via what we think now in terms of the scalar spectrum, then we would get a small tensor to scalar ratio, something like 10 to the minus 4, if I remember right. Okay. So now I'll go through the calculation in the matter bounds. And here I will first show you how you get the scalar invariant spectrum, assuming that there is a non-singular bounce, and then afterwards, if I have time, I will show you how to get a non-singular bounce.
So you have an evolution of T max to TH, That was determined, that's a parameter.
Yeah. So you see
But
that,
then the T, as it changes,
yeah, you see here I have two trajectories.
but you must have, is that T against R completely calculable?
Completely calculated.
So you have
you see-
exactly what the shape is?
Yeah. Which curve I get depends on the entropy, on the total entropy. So if I start at a fixed radius,
Does this give you an end of inflation because of the drop off there or something?
in principle, yes. In practice, we don't know how to calculate the volume. You mean end of the Hadron phase?
Well, no,
We don't have inflation.
but you have the T falling off with
Yeah,
ln R.
right.
So you're going to larger scales, and so at some point
Yeah.
there, you are going to have to go through a preheating phase where you're getting back or
No,
something.
see this, we don't need any preheating phase because this process, which is leading to the change in the equation of state, directly produces radiation.
Is it producing it effectively all the way as you move, or
No.
is it only at some
Oh.
very end?
During this phase, not at the very end, here, throughout,
It is throughout.
throughout.
But you can't, you don't have a phenomenological equation which is bleeding off into ordinary matter modes?
I can't present you one now, but that would be easy to do
Really?
compared to the difficult things to do. Okay. Any other questions right now about this string gas cosmology? Like this? Okay, so now in this scenario, so it's a symmetric evolution of the scale factor, I will start with fluctuations in their vacuum state. That's an assumption, which is not nearly as well justified in this matter bounce than it is in inflationary cosmology. They're making that assumption. So fluctuations originate as quantum vacuum perturbations, and I will show you that the adiabatic mode of fluctuations acquires a scale-down spectrum. Now, those of you who followed discussions of ectorotic cosmology will know that in ectorotic cosmology, it's the entropy mode which gets a scale-down spectrum. Here we get the adiabatic mode. Okay. So, the vacuum spectrum is not scale invariant because the vacuum spectrum, it means harmonic oscillator amplitudes for the initial perturbation. The vacuum spectrum is k-squared. So to produce a scale-invariant spectrum from a vacuum spectrum, you need something, some mechanism that boosts long wavelengths compared to short wavelengths. Now, long wavelengths spend more time outside the Hubble radius in the contracting phase than short wavelengths. And in a contracting universe, the curvature perturbation grows on superhubble scale, as opposed to in an expanding universe where it's constant. So therefore, in a contracting universe, there is a mechanism that boosts long wavelengths compared to short wavelengths. And it so turns out that if you have a matter-dominated phase of contraction, the relative enhancement of long wavelengths to short wavelength modes is exactly right to convert a vacuum spectrum to a scale-invariant spectrum. That's why this is called the matter bounce, because I need this matter-dominated phase asymmetry to convert the initial blue spectrum into a scale-invariant spectrum. And this is the growth rate of cosmological perturbations, and I will ask you to believe this. Okay. So now what we have is we have a scale-invariant spectrum of cosmological perturbations just before the bounce. Now, in various concrete realizations of a non-singular bounce, we've been able to calculate how fluctuations evolve through a very short bouncing phase. And we were able to show that on wavelengths, which are large compared to the duration of this bounce phase, the spectrum of curvature perturbations is unchanged in bounce phase. So the result is that in a matter bounce with a very short bounce phase, we have a scale-invariant spectrum of cosmological perturbations after the bounce, and therefore they bounce. So the distinctive signature is a special type, special shape in the 3-point function in the bispectrum. And the amplitude in the simplest matter balance model is between 1 and 5. So that's the FNL for the matter balance. Depending on which shape you project on, you get something which is between 5 and 1, and you get a specific shape. The reason why you get a specific shape is that if you take a general expression for the bispectrum, there are terms that depend on the time derivative of the curvature perturbation. Those are 0 in inflation and cosmology, and they are non-zero here. So you can read all about that in this figure. So now what is the big problem for the matter balance scenario? So whenever you have a cosmology based on contraction, then generically initial anisotropies, the energy density in initial anisotropies will grow very fast compared to the energy density of the things that we like. That's an aspect of the flatness problem. That's the most severe problem in any bouncing cosmology. Now, in our new ways of getting a non-singular bouncing cosmology, we are safe from that problem right around the bounce phase, but only right around the bounce phase. In naive models, you are not safe at all. In the ectorotic scenario, you are safe. So that's the biggest challenge. So now I'll just briefly present you two ways of getting a non-singular bounce. And in order to get a non-singular bounce, we either have to modify the gravitational action, or else we have to introduce a new form of matter which violates the non-energy condition. Which would you rather hear about? I don't have time for both. Modifying the Poisson-Lipschitz gravity or ghost condensation. Dick?
Lipschitz doesn't have a high degree of resonance.
Okay, then I'll go with the...
Although maybe people don't know about it enough since it's so popular.
Well, do I have 10 minutes or 5 minutes?
He says Lipschitz.
Hold on, Lipschitz. Okay. Then you can cut afterwards to ask about those comments. So now, Poisson-Lipschitz gravity was proposed without having cosmological application in mind. It was meant to be a way to quantize gravity, a way which is very conservative from one point of view. No extra dimensions, no new degrees of freedom, simply the method, the usual four-dimensional method. So very conservative approach to quantum gravity. But it's very radical in another aspect, because it gives up some cherished principles. It gives up local Lorentz invariance, and it gives up general diffeomorphism invariance. You treat time and space differently. You have a new symmetry. If the spatial coordinate becomes L times that spatial coordinate, then time goes as L to the third power of time. That's the scaling symmetry that underlies Poisson-Lipschitz gravity in three spatial dimensions. But this is familiar. These are the usual degrees of freedom that you have in gravity. The spatial metric, the shift, and the length. So, if this is the symmetry that you want to obey, plus the usual spatial diffeomorphism, plus rotational symmetry, then you write down the most general renormalizable action for gravity, and it has extra spatial derivative terms compared to Einstein gravity. These ugly terms here, which you don't have in Einstein gravity. These ugly higher spatial derivative terms give you extra terms in the Friedmann equations, provided that space has curvature, either positive or negative curvature. So this ugly gravitational action, if you write down the cosmological equations, it gives you these two nice terms. And you see they scale as a to the fourth, and they have a minus sign, independent of what the sign of the spatial curvature is. So you get something that acts as ghost radiation. So the universe starts out in the contracting phase with this dominant, this subdominant, but this grows in absolute value faster than this. So then you get to a state where this is equal to this, you get h equal to 0, and h dot is positive. So So you get a bounce, a non-singular bounce. So you can say that this term, which is given by these ugly higher space derivative terms in Rojava gravity, they act as ghost radiation, and they also terms that act as ghost anisotropic stress. And in the presence of spatial curvature, they lead to a cosmological bounce. So this is how you get a non-singular bounce. And what we've done, so one thing you have to worry about now is that since you have the usual number of degrees of freedom for gravitational fluctuations, but you have less symmetries, you have an extra propagating mode. You have to make sure that this extra propagating mode doesn't kill you.
What's implying the time vector circle? Is that
Do that by hand.
so in other words, if you shift time hypersurfaces, you get a completely different theory. Well, I mean, obviously you can just do it, but there was one fundamental choice.
That's right.
And in this story, is that fundamental choice something that's sort of labeled by the bounce? That somehow there's a simultaneity of bounce that's being imposed?
You label it, and it will determine the nature of the bounce.
So you would interpret the equations as a phenomenological set of equations that would be maybe appropriate for the region right around the bounce? Is that the interpretation?
No, I'm a little bit more ambitious here because I can use this. So I can use Rojava-Lifshitz gravity plus ordinary matter plus ordinary
No, but once
radiation.
you go away from it in either direction, presumably you try and get back as much diffeomorphism invariance as you can get, in particular, that you can shift time hypersurface.
See, no. What happens is that you have to make sure that at low energies there are no traces of the breaking of local Lorentzian boundaries. And this is indeed the truth. If, let me go back to this action, you have one mass scale.
Well, maybe that's saying the same thing.
No, you have to choose the mass scale in these higher space derivative terms to be sufficiently close to the time scale in order to get the infrared sufficiently close to local Lorentzian boundaries.
Yeah, maybe we have an offline discussion as well.
Yeah. I don't want to go to so anyway, so there is an extra propagating scalar mode, but this extra propagating scalar mode is under control in cosmology. And again, I have a couple of slides that we can skip. Then we go into the conclusions. So I hope to have convinced you that inflationary cosmology suffers from several conceptual problems, and therefore that it is worthwhile to investigate the alternatives. Now my goal was not to convince anyone that these alternatives are right, only that they are interesting. And I've shown that these alternatives give rise to a scalar spectrum of cosmological foundations, and they give rise to some predictions with which they can be distinguished from those of inflation. So this is something that deserves to grow. So, thanks.
Further questions? Yes.
So you mentioned that there is one extra degree of freedom in Rojava-Lifshitz that will be held in cosmology. As far as I understand, this degree of freedom is strongly coupled in the usual, if you want.
It is weakly coupled in the infrared. It is strongly coupled in the ultraviolet. So therefore, if you imagine that you had a matter theory which leads to inflation, you couple that to Rojava-Lifshitz gravity, then you have an ideal set of parameters of transquantum problem. Because this extra mode is strongly coupled in the ultraviolet, weakly coupled in the infrared. It's like the ideal setup. So this is a statement I made just in the context of cosmological prediction. I don't know what happens about it. This extra degree of freedom could have disastrous consequences in a black hole background. The black hole perturbation theory is much more complicated than that. What I able to say about it.
Okay, well, I suggest taking more discussions up over cookies, and I don't know if this confirmation is working or not. It certainly will be cookies. So let's talk about it again.